Okay, now if we look at, if we do this, first row times any column is just going to pick out the first number in the row, or in the column, okay? Third number times any column will pick out the third number. So the first column and the third column are going to be identical. The second row times any column is going to multiply the number here by 3. And that's going to give you the second row. So what we see is if we multiply by the 3 times 2, meaning 3 times the second row elementary matrix, it multiplies row 2, the given matrix, by 3. Okay? So the elementary matrix is obtained by multiplying the second row by 3. If you multiply that by any other matrix, it'll multiply the second row of that matrix by 3. It's the multiply second row by 3 matrix. Okay? The undo does the same thing. Well, the undo, yeah. If you switch row 1 with row 3, you get this matrix. If you multiply this matrix, switch row 1 and row 3, you can do that to the matrix we just used by multiplying it by this switch row 1 and row 3 elementary matrix. And it should be totally obvious why this is. It's going to give you the matrix where the corresponding 2 rows are switched. Okay? And that's always the case. So the elementary matrix gives you a matrix operation or matrix product that will switch the rows of any matrix you apply it to. Okay? And similarly, rows 1 and 3 are switched. Okay? Yeah. Visualize that any way you like, but that's what happens, and it's real easy to see why. Okay? Now look at the way the book proves it. Gives you insight. Yeah, look at proofs in the book so you get some insight into the way those proofs are written, because they're written elegantly.
So
Okay.
for clarification, elementary matrices are basically the matrix version of what we do for row reduction.
Yeah. Yeah, because an elementary matrix is something you get by doing a single row operation to the identity. When you do that, you get a matrix that when multiplied by any other matrix does the same row operation. And you'll see why here in a minute, because we're going to decompose a matrix into a product of elementary matrices. And then the inverse elementary matrices are easy to write down, and if we multiply those in the opposite order, we get the inverse matrix. Okay, so that's one thing we're going to do here in a minute. First, we want to, make sure we understand that these work. Look at the proof, make sure you understand why they work, but it's as simple as what we're saying. You just got to notate it. Okay, it's easy to understand why they work if you think about how the rows match up with the columns. Okay. Okay, well, anyhow, over here, the third thing is add a row to a column. So we do 4 times row 1 plus row 2. That's the matrix 1, 0, 0, 4, 1, 0, 0, 0, 1. And if what I'm saying is true, multiplying this by 2, 1, negative 1, negative 3, negative 2, 1, 1, 2, 5, should give you, well, what do I get if I add 4 times row 1 to row 2? 4 times 2 is 8, added to negative 3. Well, first of all, you're going to have the first row. We're not changing it. You'll have the last row, third row. We're not changing it. But the middle row is going to become 4 times the first row plus the second. So you're going to have an 8 here. 4 times 2 is 8, added to negative 3 gives you 5. 4 times 1 is 2, added to negative 2 gives you 2. 4 times negative 1 is negative 4, add that to 1, you get negative 3. So if I've done that correctly, the second row should come out 5, 2, negative 3. It's obvious that the first row and the last row are just the first and last rows of the identity, so the first and last rows are going to persist. What happens here? Okay? Yeah, okay. Okay, well, 4 times, okay. Second row times first column. 4 times 2, 1 times negative 3. And that ought to be familiar. That's what we did get 5, but it does give us 5, right? And it gives us 4 times 1 and 1 times negative 2. So we're adding 4 times this to this, which is what we did to get to. Okay? And again, 4 times negative 1 plus 1 times negative 3. Okay? And I'm looking at the wrong matrix. 4 times negative 1 and 1 times 1 gives us negative 3. Okay? So you see why the matrix does what it does. You see why multiplying by the elementary matrix gives you the matrix that you get from the same row operation. The matrix you get from this thing, from the same row operation. Okay? So they're all easy to understand. If you just stop and think about it, you might not even have to stop. You might totally see it right now with crystal clarity. But still, go back and think about it again to make sure. Yeah. And if you don't totally understand it now, you will. Okay, good. So, let's see what the implication of this is. Now I'm just going to do a 2 by 2 matrix because 3 by 3 takes a little while. It's no harder, just more steps. More opportunity for me to screw some up. Okay? Then I'll let you make up the matrix. So, I'm going to start with a 2 by 2 matrix. Give me a number.
2, 3, 5, 7.
A number.
Oh, one number.
Well, that sounds like one number to me. 2,357.
I don't want to use that.
Oh, I was just giving them parts.
I know, but I'll ask for one number because I want to give Mark something to do.
Sorry.
Give me a number.
2.
Okay, 2. Mark?
I'll totally pick number 3.
I was afraid you would. Uh-huh. Michael?
7.
7. Mark?
And now I'm left with 5.
Yeah, I know, he kind of reversed on me, but that's okay. Okay, now, neither of these rows is a multiple of the other, right? So I can see clearly that I can reduce this matrix to the identity. Okay? So what do? Well, we do row 1 times 1/2, giving us 1, 3/2, 7, 5. Okay? Now, our elementary matrix is we take row 1 times 1/2. Okay? The inverse of this elementary matrix Well, if we take half of the first row, then we can undo it by doubling the first row, right? So if we double the first row, we're back here. Well, that means we double the first row to get the inverse of the elementary matrix. And then we multiply this together in our heads because it's really easy, we get the identity. Okay, just to make sure we understand. Okay, then we do -7 times the first plus the second gives us 1 3/2. -7 times 1 is 0, added to 7 is 0. -7 times 3/2 is -21/2. 5 is 10/2, giving us -11/2. Okay? Make sense? No. Hopefully I did that right, but now we have our second elementary matrix is 1 0 -7 1, because we do -7 times the first row and add it to the second. If we want to undo that, we add 7 times the first row to the second. Okay? If we do 7 times this added to this, we'll get our 7 back, right? 7 times 1 added to 0 gives us 7. If I did my arithmetic right, 7 times this added to this will give us this. Okay? So let's see, that's 21. 7 times this is 21/2. 21/2 -11/2 is 10/2, which is 5. So I've checked that out to my tentative satisfaction because I'm totally capable of screwing up. But so adding 7 times the first row to the second undoes it. And that's what we have to do. And then if I multiply these matrices, easily verified, this times this gives us 1, this times this, which is 0, the matchup gives us 0. This times this gives us a -7 and a 7, which is 0. And this times this, the only thing that doesn't match up with 0 is that 1, which matches with 1, gives us a 1, gives us the identity. If you didn't understand that, just do it yourself, make sure you see it. Okay? Okay, so, I'm talking fast. If you don't understand, it's all right. It's not a matter of intelligence whether your brain processes auditory information quickly. Okay? But I said it fast because it's something easily verified for yourself. Okay. And then what's the last thing we have to, well, not the last thing, we've got to multiply this by -2/11, right? So it's going to be second row times 2/11. Okay, that's going to give us 1 3/2, 0, 1. It should be -2/11 to get to 1. Okay? What's our elementary matrix? Well, it's E3 equals 1 0 0 -2/11. So the E2 inverse equals 1 0 0, the reciprocal of what we multiplied by here, which would be -11/2. Okay? So that's real straightforward. Then we just have to do first row plus 3/2 times the second. Not plus, but minus 3/2 times the second. Which will give us 1 0 0 1. There's the identity. So we reduce this matrix to the identity. Okay? And our E3 is what? It's 1 -3/2 0 1, because we're adding -3/2 of the identity of the second row of the identity to the first. Okay? and E1 or E3 inverse is what? It's 1, 3 halves, 0, 1. Well, we add 3 halves the second row to the first. Again, check, multiply these two, make sure you have the identity, make sure that you're on the right track. They can't necessarily do that at every step when you're doing a bigger matrix. If you do really big ones, you let computer algebra do the reduction. What you need to know is how the elementary matrices work. They're very easy to write down. Of course, they're very easy to write down with a silly mistake. Okay? And you don't rely on yourself to do anything more than about a 3 by 3. You can expect to get a good result. Okay? And if you are, you want to do it twice on different days and then compare. If you got the same thing twice, maybe you're right. There are other ways to check. And what you then do is just what we're going to do. Okay, so what this says is then that we start with 2, 3, 7, 5. We multiply that by E1.
With that last row of that elementary matrix be 0, 1.
Yeah, it is. I was having trouble with that. I was about to come to that conclusion. I said, wait a minute, we got to get 7, 5. I'm getting 49, 25, so, or worse. So anyhow, there it is. Okay? So that's E1 times this. Okay? Then, E2 times that is 1, 3 halves. Sorry, 1, 0, I'm looking at the wrong matrix. 1, 0, negative 7, 1 times 2, 3, 7, 5 equals 2, 3. Uh-oh.
Is it 1, 3 halves?
Yeah, it's got to be 1, 3 halves. I'm just being careless with what I look at. 1, 3 halves, 7, 5. Okay? Which gives us 1, 3 halves, 0, negative 11 halves. Yeah. Okay? And you can do the multiplication yourself and verify it. I'd like to give myself a little more room. It doesn't really fall if I go too far. Okay? Then, okay, well this is E2 times E1 times the original matrix. We multiply that by E3. And you notice that the matrices we're getting here totally match these matrices. Okay? And I'm trying not to look at those matrices and copy them down. I'm trying to really do the multiplication, which is why I keep looking at the wrong matrix. Okay? Times okay? So we're just chaining the elementary matrices. There are going to be 4 of them. They're all very easy. Okay, so E3 is 1, 0, 0, negative 2 elevenths, which we multiply by this, 1, 3 halves, 0, negative 11 halves, giving us 1, 3 halves, the 1, 0 just picks that up first, and then 0 and negative 2 elevenths times negative 11 halves is 1. Okay? So that seems to work. And then we do keep having to write this smaller because I want to keep things moving along. And we multiply by the 1, negative 3 halves, 0, 1. Multiplied by this. And 1, negative 3 halves, well, that's going to give us 1. And 1, negative 3 halves times the 3 halves and negative 3 halves we get here. Sorry, what? 1, negative 3 halves times the 3 halves, 1 gives us 3 halves minus 3 halves, which is 0. And then 0, 1, which is going to pick out the second row. That's going to give us 0, 1. Okay? So it all worked. Well, now, if we do E4 inverse times this, okay? We could multiply it out, because we'd just be doing E4 inverse times the identity, okay? Which is just going to be E4 inverse. That's E3 there, E1, E2, E3. I multiplied this last, I labeled this last one as E3, it should have been E4, okay? So originally, when I wrote these down, I was a little careless. I labeled this one E3 and this one E3 inverse. Should have been E4, E4 inverse. So I just made that change. I looked over there and I saw E3 at the end. I said, well, I knew I had 4 matrices. So I found it. Okay? Now, I could multiply this out to verify it, and it's a good idea to do that, to convince yourself at least one time in your life. Okay? But once you've got it locked in, you understand it, and you can always think back to it. And if you ever can't think back to it, you better go do another one. Okay? So we have E4 inverse times this whole string. Well, matrix multiplication is associative. Okay? I'm pretty sure I didn't give you that as a proof that you should do. I'm pretty sure your book didn't write it out. Maybe they did, but it's pretty long. You know, I mean, just lots of summations. If I was doing it, I think I'd be tempted to do it for 2 by 2 matrices and use induction. But I mean, it's possible right out. It's just long and messy, and it works. So anyhow, matrix multiplication is associative. Well, I haven't even grouped these because I know it's associative. Okay? And I know that each of these, well, I'm just using the fact that it's associative. It's not commutative. Okay? But here we've got E4 inverse next to E4. So I could rearrange this as this. Okay? And what's E4 inverse times E4? Well, every time I did this, I said, well, you multiply these out, they give you the identity, so E4 inverse times E4 is the identity. So I've got this, which just equals times 2, 3, 7, 5, right? Well, it's getting a little tedious, but it's worth writing out because it's real important. Okay? So, E3 times E4 inverse times E4, etc. Equals, to be really meticulous, you do E3 inverse times E4 inverse E4, E3 E2 E1 times 2, 3, 7, 5 equals this, because you know this is the identity, and when you multiply it by anything, whichever matrix that's left or right you associate it with, you just get that matrix. I'm going to put 3 dots because there's an intermediate step. Well, what happens here? What are we going to do with this?
Becomes the identity.
E3 inverse times E3 is the identity, and the identity times the rest of this is just the rest of this. So I'm going to, I'm skipping those steps now, although I put them in here. They get pretty tedious to write down, and once a pattern's established, it's very clear that this is going to be then so when we get down to this, what do we end up with?
The original matrix.
We get the original matrix because there's an identity which can then be discarded. I mean, group it with whatever is next to it, and it becomes whatever's next to it. And then same thing, same thing, same thing. You don't want to have to write it down for all steps. You find a way to clearly notate it with a few words that show you that no matter how many of these you have, you can always do this. So that equals this. Okay? Well, I don't have it up there anymore. This is what you did to reduce this matrix to the identity. So this product is equal to the inverse. Okay? Furthermore, I'm gonna write it out in all its glorious detail. Then this product, which you know is equal to the original matrix, is just the product of the inverse matrices times the identity. And that equals the original matrix, right? That means the product of these inverse matrices is your original matrix. So our big conclusion, and I'm going to generalize this, if you have m elementary matrices, reduce matrix A to the identity for any n. Of course, these will be n by n, and A will be n by n, right? And the same thing happens. This series of matrix operations is the inverse. It's got to be in reverse order because E1 is the first one that multiplies A, right? And E2 is the second one that multiplies A, so you got to put them in this reverse order. Make sure you understand that. No mystery to it. If you understand the example, and the example is really easy to understand. Okay? So we have this, and that's equal to A inverse. And